So, we would continue with our discussion on the convection transfer equations in this class, and what we are planning to do here is to look at the three equations that describe momentum, heat and mass transfer inside the respective boundary layers, and we would like to see what are the similarities between these three equations, what are the boundary conditions, are those conditions, boundary conditions similar, and if we can express these three equations along with their boundary conditions in such a way that the equations become identical as far as their forms are concerned, as well as the boundary conditions will also be the same. So, can we do that? So, the first step what we have done in order to achieve that was we identified first what are the three equations and what are the dimensionless parameters which arise automatically in those equations. So, we started with a two-dimensional steady state flow assumption, and the approximations that we have made are incompressible flow with constant properties. The body force, effect of body force is insignificant. It is a non-reacting system, and since it is non-reacting system, no species is produced or destroyed. So, therefore, n dot A would be equal to 0, and there is no energy generation by whatever means inside the system. Therefore, Q dot, the heat generation per unit volume, is also 0. And since it is mostly low velocity forced convection system, so the viscous dissipation which arises only when the velocity gradient or the velocity itself is very high. So, this is also negligible, and therefore, the dissipation function phi that we have defined in case of energy transfer would also be 0. The approximations that we have used for velocity boundary layer is that the axial component of velocity is very large compared to the component of velocity which is perpendicular to the direction of flow. The gradient of velocity with the gradient of axial velocity with distance from the solid wall is significantly higher compared to the gradient of the velocity with respect to x, the gradient of the v component of velocity with respect to y, and that of with respect to that of x. For thermal boundary layer, we understand that since for all these cases these conditions arise since the thickness of the boundary layer is very thin. So, therefore, the change in velocity over the vertical distance from the wall will overshadow the change in temperature with respect to the axial positions, and similarly the change in concentration of species A over the thickness of the boundary layer will be greater, significantly greater than the species concentration change with respect to the axial distance. So, these equations together form the concentration boundary layer, which would help us in resolving the corresponding equations by cancelling some of the terms which are not going to be relevant here. So, the continuity equation for x transport of moment continuity equation, and the x momentum equation would simply be these advection terms. This is a pressure gradient, axial pressure gradient term, and then we have a diffusive transport of momentum in the y direction. The energy equation would simply again be the advection terms on this side, the property which is alpha, the thermal diffusivity, and it is a variation, it is del to T by del y square. There is no Q dot and phi is 0. For the concentration boundary layer, we get the similar expressions. So, you see that all these changes in concentration or that of temperature are associated with a velocity. So, therefore, these are convection terms, together they called advection terms. So, there are advection terms on the left and diffusion term on the right. So, we have these are the advection terms in the transport equations, where these are diffusive transport of momentum, energy and species, and the corresponding properties are the kinematic viscosity, which is mu by rho, the thermal diffusivity, which is k by rho Cp, and the mass diffusivity, which is dAb. So, with this starting point, I think we are now in a position to look at what the boundary layer similarity, and in order to do the boundary layer similarity, we are first going to normalize the convection equations that we have written over here. So, you would like to express them in terms of dimensionless forms, and the dimensionless the non-dimensionalizing parameters are x star, where this is the length of the plate over which length of the surface, it is a length scale, axial length scale. Y star is y by L, u star is u by v, where v is the approach velocity. So, this v is the approach velocity, and v star is similarly defined. The dimensionless temperature is T minus the temperature of the substrate, solid substrate, divided by T infinity minus Ts, where T infinity is the temperature of the bulk fluid. And in a similar way, Cs star, that is the dimensionless concentration gradient, is also expressed as Ca, which is the species concentration, and which we understand is going to be, can be a function of both, would be a function of both x and y, or in dimensionless forms x star and y star. So, it is Ca minus Ca infinity divided Ca minus Cas divided by Ca infinity minus Cas. The reason that all these equations are non-dimensionalized is that when you non-dimensionalize, not only everything the equations become more stable, they vary between the limits of 0 to 1, as in the case of, let us say, velocity, where the velocity is going to be 0 at the solid liquid interface, and it is going to be equal to the free stream velocity. So, the range of dimensionless velocities will always be from 0 to 1, and similarly the range of temperature and concentration would also vary between 0 to 1. There are other advantages of non-dimensionalizing any governing equation, is that for some cases you would see that certain numbers would appear, the collection of numbers would appear which are dimensionless and which relate to, which essentially specify the process. They tell us something about the dynamics of the process, or they tell us something about the nature of the process, the importance of each of the terms, different mechanisms which are present in any process. So, it is always advisable to non-dimensionalize a set of governing equations to get more insights into the physics of the problem. So, that is what we have done, and then based on the non-dimensionalizing parameters that I have just described, the previous three transport equations, the equation of momentum, the equation of the thermal energy equation, and the species balance equation, in the momentum, thermal and the mass transfer boundary layer, they are non-dimensionalized, and what we get is the following form of the equation. So, the equation that you are going to get, so the conservation equations would take this form, where u star, v star, x star, y star, this we have already defined. So, this is the pressure gradient term, this is the energy equation, again the same thing, same form as before, but in dimensionless forms, and here we have the species transfer equation in this. Now, note the terms that I have circled in red, all these are dimensionless number. These are the so called similarity parameters, which would tell us a specific characteristic of the transport process. For example, this nu by VL can be expressed as nu by VL is nothing but mu by rho VL. So, if you see this, this is nothing but 1 by Reynolds number. So, the Reynolds number therefore appears in any relation or correlation that you can think of in the case of momentum transfer. So, a momentum transfer will most likely will have the Reynolds number, the corresponding Reynolds number would be the corresponding dimensionless number will be Reynolds number. So, this nu by VL is nothing but the Reynolds number. Similarly, if you look at if you examine alpha by VL, alpha by VL is nothing but mu by rho times 1 by VL. So, this can be expressed as the kinematic viscosity, this I will express it in a different way as this is nu by VL times alpha by nu. So, this is the thermal diffusivity, this is the velocity and it is the length. So, I bring in the nu in here, and divide it by nu at this point. So, what we have here is then as like this becomes 1 by Reynolds number, and this is alpha is k by rho Cp, and this is mu by rho. So, rho and rho cancels, what you get is k by Cp mu, and we understand that k by Cp mu, or rather Cp mu by k is Prandtl number. So, this is 1 by Prandtl number. So, this entire term what appears over here in the energy equation is nothing but 1 by Reynolds number times Prandtl number. So, the circle term, which has to be dimensionless, since all other terms in this equation are dimensionless, this can be rearranged. This is the thermal diffusivity. This can be rearranged as nu, which is the kinematic viscosity, by VL times alpha, which is the thermal diffusivity, by nu, and they are nothing but Reynolds, a combination of Reynolds and Prandtl number. So, when we deal with heat transfer, you would expect that these two numbers would automatically appear in any relation or correlation that you can think of for heat transfer. So, you see there is a simple process of non-dimensionalizing the governing equation tells you so many things, that if you have to fit experimental data with the other parameters of the system, your natural choice for dimensionless number is something which is being predicted, which is being projected by the governing equation itself to be Reynolds and Prandtl number. Similarly, if you look at the mass transfer boundary layer, so by simple intuition you can say, and you can verify that by looking at the red circle that I have drawn across, I have drawn along the bunch of dimensionless quantities. The Reynolds number would obviously be there in mass transfer as well. However, the Prandtl number is to be replaced by its equivalent in mass transfer. So, the equivalent of Prandtl number is Prandtl number in mass transfer is Schmidt number. So, the circled one, the circled term that I have over here as dAb by VL, it can simply be expressed as nu, the kinematic viscosity, by VL times dAb by nu. So, this, as we have seen before, from here is nothing but the 1 by Reynolds number, and this one dAb by nu is dAb mu by rho. So, nu is mu by rho. So, mu by rho dAb is nothing but the definition of Schmidt number. So, therefore, this is going to be 1 by Re times Sc. So, the three terms that I have circled with red over here, the so called similarity parameters, which I can write for this case is going to be Reynolds number based on the length of the surface, length scale, and for the thermal one, the thermal boundary layer, it is going to be Reynolds number and Prandtl number, and for the case of mass transfer, it is going to be Reynolds number and Schmidt number. So, these are the various similarity parameters that appear in the conservation equation when you non-dimensionalize them. Now, let us look at the boundary conditions that we have in here. Let us first think about what we have in the case on the wall. Due to no slip condition, U star at y star corresponding to 0, which is essentially on the surface, U star would be 0 and V star would also be equal to 0. At the free stream, the velocity, the dimensionless axial component of the velocity would be equal to u infinity divided by v, and so this is the approach velocity and this is the free stream velocity, and for the special case of flow over a flat plate, u infinity would be equal to v, and therefore, u star x star infinity for the case of a flat plate will be equal to 1. But in order to keep the system, in order to maintain the generality of the solution that we are going to get, I have kept u infinity and v at this point they may not be equal to each other. So, the dimensionless velocity at the free stream would simply be the ratio of the free stream velocity divided by the approach velocity. Similarly, when we look at the expression, look at the dimensionless temperature difference over dimensionless temperature difference at the free stream, which is defined as, so T star is defined as Ts minus T by Ts minus T infinity. So it would simply be equal to 0 at the free stream, because this T is going to be equal to Ts, and at the wall, and at the free stream its value is going to be equal to 1, since the numerator and the denominator would cancel each other. Similarly, when we have the Ca star, that is the dimensionless concentration at the free stream, this is the definition of Ca star which we have used as Ca minus Cas by Ca infinity minus Cas. So on the surface of the solid, Ca would simply be equal to Cas, and therefore Ca x star 0 is 0, and Ca star at x star infinite, that is at a point far from the solid plate, its value is going to be equal to 1. So these are the three equations, the corresponding boundary conditions and the values of the expressions for the similarity parameters that appear that appear when you non-dimensionalize the system. So we wanted to see how can we say that the solution of these three equations would be identical. If we can somehow establish that the solution, without actually solving them, that the solution of these equations would be identical because of some special form of the boundary conditions and some values of the dimensionless numbers, then we have established some sort of an analogy between them. So that would be the next task which we are going to do. So the first thing that we are going to do is we are going to write what are the functional form of the solutions. We are not going to actually solve them, but we are going to look at the functional form of the solution. So if you see the first equation, if I could solve u star, what would u star be a function of? So u star, if you see this equation, u star would definitely be a function of the independent variables, which are x star and y star. It is also going to be a function of what kind of pressure gradient you have in the system. So u star is going to be a function of the pressure gradient dp star dx star, and definitely u star is going to be a function of the dimensionless parameter that has appeared in the governing equation. So the functional form of u star would contain, we still do not know what that functional form is, but it should contain, if we could derive that, we know that it would contain x star, y star, dp star and the Reynolds number. So the functional form of u star, if I call it as function 1, we do not know what that function 1 is, but we do know now that it should contain x star, y star, Reynolds number and dp star dx star. So this is obvious, but when you look at the form of the equation. So we are more interested not in velocity, but on the shear stress at the surface. So the shear stress at the surface, that means I am specifying the value of y star, which is at the surface, means it is going to be y star equals 0. So this the functional form of that tau s would simply be equal to mu, if it is a Newtonian fluid, del u by del y at y equal to 0. This is the expression for shear stress, and if we non-dimensionalize this, again the non-dimensionalizing parameters are x star equals x by L, y star equals y by L, u star is u by v, similarly v star is v by v and so on. So this, if I non-dimensionalize this part, then it would simply be equal to mu times V by L del u star by del y star at y star is equal to 0. And we know that the friction coefficient, the engineering parameter of interest, is defined as tau s by half rho v square. Okay. So, if this is the case, so when you bring in this tau s, expression of tau s in here in CF, it would simply be equals 2 by Reynolds number del u star by del y star at y star is equal to 0. Okay. So, I already know what is the functional form of u star. So, this CF is going to be equal to, if I define the functional form of this as f2, it is going to be a function of x star and REL. I will go through it once again. What I have done is I identified from the equation that is given, that we have seen, is u star is going to be a function of the two independent variables, namely x star and y star. It is going to be a function of the pressure gradient present in the system, which is dp star dx star, and it should also be a function of the Reynolds number of the flow. So, my u star is some function that I call as f1, and the f1 should contain the variables x star, y star, the imposed condition dp star dx star, and the dimensionless number, which is Reynolds number. Then I decide to find out what would be the expression for the friction coefficient. We know that friction coefficient is defined as tau s, which is the wall shear stress, divided by half rho u square. And what is tau s? For a Newtonian fluid, tau s is simply equal to mu times del u del y at y equal to 0, the velocity gradient at y equal to 0. So, this velocity gradient del u del y, I express them in dimensionless form. So, what I get for tau s is simply this form, where everything is expressed here in dimensionless form, and mu v by L, the v and L appear because I have divided y by L, and therefore I have to divide this of L as well, and u is simply non-dimensionalized. If you look over here as u by v, so it appears in this way. So, CF, which is tau s by this, would simply be equal to 2 by REL del u square by del y star at y star equal to 0. If you look at this expression, since I have specified the value of y star to be equal to 0, therefore, the function that I am going to write for f2 will not contain y star, because I am evaluating this at a fixed value of y star. Therefore, I have fixed y star. So, therefore, this is no longer a variable in the expression. Therefore, f2 should not contain y star, but I did not say anything about x star. So, my x star appears over here. I did not specify what is Reynolds number. So, Reynolds number appears in the functional form. Y star did not, I specified, so y star does not appear in here, but at the same time dp star dx star does not appear in this expression, and so for that I write a specialized condition that for a prescribed geometry, where the geometry is known to me, where I am aware of what would be the geometry. So, if this is the surface, whatever be the shape of the surface, this is the boundary layer, I can find out what is dp dx by analyzing the flow outside of the boundary layer. And since my pressure is a function of y only, so if I can calculate what is P1 and what is P2, then if I can calculate P2 minus P1 by delta x, where the distance between them is delta x, so that means dp dx can be calculated based on inviscid flow theory outside of the boundary layer. we realize that inside the boundary layer the flow is viscous. So, Navier-Stokes equation will have to be solved in order to obtain what is the pressure difference pressure gradient between these 2 points, but I need not do that because I understand my pressure is a function of y only. So, whatever be the value of dp dx at this point outside of the boundary layer would be the value of dp dx inside the boundary layer. And since the flow outside the boundary layer is inviscid, so Bernoulli's equation or some such equation can be used to obtain what is P2 minus P1 by delta x. So, if I prescribe the geometry, if I know what kind of a geometry I am dealing with, then I have inviscid flow theory that can independently give me what is the pressure difference, what is the pressure gradient. So, as long as the geometry is known, the pressure gradient between 2 points in the inviscid flow field can be obtained easily without having to solve Navier-Stokes equation. So, the moment the geometry is prescribed, the pressure gradient is known to me, and since the pressure gradient is known to me, therefore, the pressure gradient does not appear in the functional form F2 that I have written. So, F2 does not contain the y star, since I have specified the value of y star to be at 0, and F2 will not contain any dp dx if I prescribe, if a priori I tell what kind of a geometry we are experiencing, we are encountering during the flow. So, dp dx is known to me. Therefore, the expression for Cf should only contain the F2 should only contain x star, the distance, and Reynolds number. When in a similar way, I am going to find out what my T star would contain now. So, let us say that T star is some function, and I am looking at this equation and trying to see what would be the functional form only, not the exact form, what would be the functional form of T star. So, T star must contain the independent variables x star, y star, and this parameter, which is Reynolds number, and since u and v are involved, so T star would contain all the functions, all the parameters which are functions which are used in expressing u star and v star. So, therefore, my T star would be a function of x star, y star, Reynolds number, dp dx, dp star dx star. All these were there for u star. Now, since in the equation that I have, T star is a function of u star, v star, etc., and so on. Therefore, my expression for T star would contain all these which were there in the expression of u star. So, my F3 would contain x star, y star, Reynolds number, and dp dx. If you see this equation, the governing equation, one more time, you would see that T star would contain not only the functions of corresponding to u star, it should also contain what are the similarity parameters. So, alpha by VL is nothing but Reynolds times 1 by Reynolds times Prandtl number. So, it will not only be a function of Reynolds number, it would also be a function of Prandtl number. So, therefore, the temperature expression would contain Prandtl number as well. So, that is the only difference which we have in the functional relationship of T star. We still do not know what F3 is, how x star is connected with T star, or how Reynolds number is connected with T star, and so on. But in functional form, this is the form that we have. And as before, as in the case of momentum transfer, we wanted to find out what is the shear stress and shear stress coefficient. So, in the case of heat transfer, it is going to be whatever be the heat that is lost, whatever be the heat transfer from the solid surface, which would simply be equal to Kf del T del y at y equals 0, that is at the interface between the solid and the liquid, and we know that this heat which is lost from the solid surface is also equal to h times Ts minus T infinity, where this h is an engineering parameter of interest, which is nothing but the convective heat transfer coefficient. So, this is Newton's law, and at the solid liquid interface, the Newton's law of cooling, the convective heat transfer is equal to the conductive heat transfer, and therefore, this equation defines what is the convective heat transfer coefficient that we have described before. So, this would simply give you H equals minus K F del T del y at y equals 0 divided by T s minus T infinity. So, that is the classical definition of the convective heat transfer coefficient, which is the conductive heat flux divided by the temperature difference, which comes from the equality of convection and conduction at the liquid vapor interface. So, this I am going to non-dimensionalize these T, y, etc. So, H would simply be equal to minus K F, just a non-dimensionalization, nothing else, T infinity minus T s by what I have over here is T s minus T infinity, and this would simply be equals del T star del y star at y star equal to 0. So, nothing new in here, I am simply expressing this T and y in dimensionless forms. So, these two will cancel and the minus sign would also disappear because of the nature of this. So, what you have then H L by K F, that we know as Nusselt number, H L by K F. The same way we have obtained C f, the expression of C f in the case of momentum transfer, we are getting what is Nusselt number in here, which you would see is del T star by del y star at y star is equal to 0. So, the correct classical definition of Nusselt number would be it is the dimensionless temperature gradient at the solid fluid interface. And now you can see why Nusselt number is equal to del T star by del y star, where T star is the dimensionless temperature and y star is the dimensionless distance from the solid wall. So, when you find out del T star by del y star, the way we have defined T star and y star, you precisely get what is nothing but the expression for the Nusselt number. So, we look at this and we are trying to see what is Nusselt, the functional form of Nusselt number. So, let us call it as F4. So, if you see the functional form of Nusselt number would contain X star, Reynolds number and Prandtl number. Since we have specified the value of y at y star equal to 0. So, y star does not appear in the functional form, and since we have we know what is the, so this is for a prescribed geometry, and since the geometry is known to me, so therefore, dp dx can be obtained independently, and that is why it does not appear in this expression, and therefore, Nusselt number is equal to X star Re PR. If you find out what is the average value of Nusselt number, so if this is the average Nusselt number, the Nusselt number that I have obtained over here is, here the H is the local heat transfer, convective heat transfer coefficient. If I have to find out the average value of Nusselt number, I will simply integrate this expression over the entire length of this substrate, and therefore, that would is denoted by the average value. The bar over here denotes the length average value of H L by K F, and which if I call it as F5 function 5, it will only be a function of Reynolds and Prandtl number. So, since I have integrated over this x, therefore, the x does not appear in my functional relationship anymore. So, this is a fundamentally important result, which simply tells you that the average value of Nusselt number will only be a function of Reynolds number and Prandtl number. Now, you try to recall all the expressions of convective heat transfer, the relations and correlations of convective heat transfer that you have come across in your heat transfer, in your study of heat transfer. So, in all the expressions that you can think of, were or are functions of Reynolds and Prandtl number. So, starting with Dietz-Boulter equation or any equation for convective heat flow, the relations are always expressed in terms of Reynolds number and Prandtl number. And now you know why that expression of Nusselt number should always contain the Prandtl number and Reynolds number. So, since we have done this for heat transfer, I can very quickly do it for mass transfer as well. So, the mass transfer C A star, and then again I am looking at the expression which looking at the relation which is this that I have written. The C A star would be a function of x, y, Reynolds, Schmidt and dp dx, the same way it was done for the temperature. So, it is going to be a function, let us call it as a f6 x star, y star, Reynolds number, Schmidt number and dp star by dx star, exactly the same way. So, I am not spending any more time, and we are more interested in finding out what is the flux, mass flux, which is minus dAB del Ca del y at y equal to 0, which the same way as in convective heat transfer would be Cas minus Ca infinity, and this Hm is the convective mass transfer coefficient. So, your definition of Hm would therefore be minus dAB del Ca del y at y equals 0 divided by Cas minus Ca infinity directly from this, in which when you non-dimensionalize this Hm would be dAB by L del Ca star by del y star at y star equals 0, and you bring this to other side. So, it becomes Hm L by dAB, which in mass transfer terms is known as the Sherwood number, which has the same significance as Nusselt number in heat transfer, would be simply del Ca star by del y star at y star equals 0. So, Sherwood number is nothing but the dimensionless concentration gradient at the interface. So, your Sherwood number would simply be a function f, I call it as f7 of x star, REL and SC, and same again for a specific prescribed geometry. So, if you look at this, del Ca del y would not contain any y, it should contain Reynolds number, Schmidt number, and since a geometry is specified, so dp star dy star would also not appear over here. And the length average value of Sherwood number, which I call it as SH bar, which is the length average value of the convective mass transfer coefficient by dAB, would be a function of Reynolds number and Schmidt number. So, if you compare these two expressions, average value of the Nusselt number is average value of the convective heat transfer coefficients L by Kf is a function of Reynolds and Prandtl number. Here you see, using the same logic, we obtained the average value of the Sherwood number is equal to the average value of convective mass transfer coefficient, and in functional form it should only contain Reynolds and Schmidt number. So, therefore, we are slowly coming to a point where we start to see a picture is going to emerge, is slowly emerging, where we can see that all these are coming into place and they are becoming similar. The expression of Nusselt number, the expression of Sherwood number and the expression for the friction coefficient, they all start to look like the same. So, they are converging to a point. Now, what we need to do, what we have to identify in the coming two classes is what are the special conditions which we must identify, which we must specify, so that all these relations at some point of time would become identical, and therefore, any relation of mass transfer can be interchangeably used as the relation for heat transfer, provided we substitute the similarity parameters relevant in heat transfer by the similarity parameter relevant in mass transfer. So, that is what we will establish in the next class.